Hi everyone, welcome to the University of York School of Physics, Engineering and Technology's winter webinar series. My name's Dr. Chris Murphy. I'm a plasma physicist, a laser plasma physicist, in fact, at the Plasma Institute here at the University of York. I'm also the admissions tutor, so I can help anybody. So I welcome in particular to those of you who are applicants who have recently submitted your application to join us here in physics or engineering at the University of York. Now, for tonight's event, it'll be with a great pleasure to introduce Dr. Phil Hasnip, who is a lecturer and research software engineer at the School of Physics, Engineering and Technology here at the University of York. He grew up in the 1980s, where he learned physics at school, but computer programming used on his 8-bit Sinclair ZX Spectrum. That's for the older people in the audience. And he now combines both interests in lead develop of CASTEP software, which uses quantum mechanics to model and predict new materials and chemicals. So really using the sort of fundamental physics, the stuff that's kind of the quirky, crazy quantum physics, in order to make real developments in both materials and chemicals, and all kinds of applications of this, including things like heat recovery for things like to help the fight against climate change, and even medical applications as well. But I'm not going to say any more about what he's going to talk about because he's here to do that himself. So let's introduce Phil Hasnip, who's going to talk all about quantum mechanics and the applications which help us develop new materials. Take it away, Phil.
Thank you very much, Chris. Yeah, so I'm going to tell you a little bit about designing new materials with quantum mechanics, and we're going to start really with quantum mechanics. When I say materials, a lot of people think about wood and metal and plastic and things like that. But when a physicist says materials, they really go back to where the word comes from. We're thinking about simulating matter. So it really might be that we're just simulating anything pretty much in the world around us. It could be a technological application. It could be a medical application. It could be even our bodies. So some of the things, if you were at Agnes' webinar, you will have seen about DNA. Some of those things as well, we might be interested in simulating with quantum mechanics. The reason we can do this is because pretty much everything we see around us is made of atoms. Now, atoms are very small. If you think about your own hair, sort of average human hair is about 1/10 of a millimeter wide. And that 1/10 of a millimeter is something like 1/3 of a million atoms. So if you think about taking a hair of your head and dividing it into 300,000 parts, that is roughly one atom. So there are an awful lot of atoms in a human hair. They are really very small. 1 milliliter of water has 33 quintillion atoms, which is a lot of noughts, as you can see. They're made up of a nucleus and some electrons. And in order to understand what they are going to do, and we're going to model this from what we call first principles, which means we're going to try and understand what this is going to do without knowing what it does beforehand. So there are other methods where if you know you've got a gas, you could model it with some special equations for gases. If you know it's a metal, you could model maybe the conduction, the electrical conduction with some different equations. But I want to be able to take a material nobody has ever made before and predict what it will be, to predict whether it's a gas or whether it's a metal or whatever it might be. And to do that, we use quantum mechanics. And in quantum mechanics, one of the key ideas is that we can't just take a particle and say, there it is. So on the left side here, we've got ordinary physics, and I've plotted space along the bottom. It's going from -4 to 4 in some units, and the probability density of finding a particle there. And in ordinary physics, if the particle is at the origin, at 0, what we mean is there's 0 probability of finding it anywhere else. And then when we get to 0, there's suddenly probability 1. That's where it is. But in quantum mechanics, that isn't true. If I say the particle is at 0, what it normally means is there's a probability distribution. The average is 0. Probably, I mean, the most likely place to find it is 0, but that's not necessarily the only place that I might find it. So in quantum mechanics, the probability distribution, which is strongly related to the wave function of quantum mechanics, is spread out in space. And to find the wave function, we solve what's called the Schrödinger equation. And the wave function itself is a function, just like you'll have met in maths before, a function not of one variable like x, a function of x, y, and z for each particle. So I've wrapped up x, y, and z in a vector here, r, and I've got r1, that's the position of the first particle, r2 for a second particle, r3, and so on for as many particles as I've got. And the wave function contains effectively all the information about the particles. We can get all the information we might desire once we've computed the wave function, or we understand what the wave function is. So let's suppose we calculate the wave function just for one particle, and I'm going to take a very crude approximation. I'm just going to say, let's split space up into basically 10 points along x and along y and along z. So I've got a sort of sample space at regular intervals. Because I've got 10 points along x, 10 along y, 10 along z, my total, that forms a grid, and my total number of points is 10 times 10 times 10, so that's 1,000 points in total. How big does that mean the wave function is? Well, it's quite common to use 16 bytes of memory per number. This is what's known as double precision for a complex number, which the wave function is normally. So we need 16 bytes per number, and we've got 1,000 numbers, so that's 16,000 bytes, which is 16 kilobytes effectively. It's very small. 16 kilobytes, that's not a problem. When we have two particles, well, now it's slightly more complicated because the wave function, remember, depends on the positions of all the particles. So now the wave function is a function of r1 and r2. And what that means is for every possible position of particle 1, so every value of r1, I have all possible positions of r2, and the wave function might have a different value for each of those. So if I need 1,000 points for my first particle, when I introduce a second particle, I need 1,000 points for that for every one of the 1,000 points of particle 1. So that means I now have 1,000 times 1,000 points, so 1,000,000 numbers. Now I still need 16 bytes per number, so that means I've got 16 million bytes, 16 megabytes, which is still pretty small. But you might already be able to see where we're going with this. If I have a third particle, the wave function has a value for every possible position of particle 3 for every combination of particles 1 and 2. So now I've got all possible combinations of where these three particles might be in my wave function. So I need 16 bytes per number, and they need 1,000 times 1,000 times 1,000, 1,000 cubed numbers, which is 1,000,000,000. And so now my wave function is not 16 megabytes, it's 16 gigabytes. And now I'm starting to care, because 16 gigabytes I would notice on my phone, or even on my computer. I would notice if I had a file or something in my memory taking 16 gigabytes. So let's think about this. Whenever I add a particle, the wave function grows because it depends on one more particle than it did before. And every particle I add means a new 1,000 times amount of data. Okay, I need 1,000 points for this particle, but for every combination of the particles I've done before. So we've already seen if one particle it was 16 kilobytes, and for two particles it was 16 megabytes, and for three particles it was 16 gigabytes. So for 4 we get 16 terabytes, for 5 16 petabytes, 6 16 exabytes, and 7 16 zettabytes. 16 zettabytes is a significant fraction of the entire storage in all of the data centers in the world. So if we were to try and do 8 particles here, we'd be in trouble. We would need more storage than the entire global data storage. And that's a bit of a problem because if I'm thinking about these 8 as being, for example, electrons, 8 electrons is not actually very many. That's only one atom of oxygen, 8 electrons, and that's just one atom then. I don't really get much by way of a material if I can only model one atom. Or equivalently, I could have maybe 8 hydrogen atoms, but still, I'm not going to make any materials out of only 8 atoms. So how can we make quantum mechanics an easier problem? Well, there are 3 things we're going to focus on. One of them is we could use quantum mechanics for the electrons. I've already hinted at that. I said oxygen would need 8 electrons. But normally you'd think, oh, but there are nuclei as well. Don't I need quantum mechanics for that? I'm going to concentrate my effort on the lowest energy state. You'll see why that's a good and useful thing in a few moments. And quite possibly the most important thing, as far as I'm concerned, is I'm going to get a computer to do all the difficult stuff. Particularly all the boring, difficult stuff. Interesting, difficult, I like to do, but boring and difficult, I get a computer to do. So let's think about using quantum mechanics for the electrons, first of all. Do you remember that I said in quantum mechanics, the probability is of a particle being at any one place, it's not a single spike somewhere, it's spread over space. And how spread out it is depends on the particle mass. And in particular, the heavier it is, the more massive, the less spread out it is. So if we look at the wave functions and the probability distribution, which is basically the magnitude of the wave function squared, if we start with a low mass, we might get this. So the particle is most likely to be at 0 still, but quite likely to be at ±1 and ±2. And now let's look at make the particle a bit heavier. If I make it heavier, the wave function gets a little bit more peaked around 0. And as we make it heavier and heavier and heavier and heavier, the wave function gets more and more strongly peaked around the position where we would classically say that it is. So in this case, I've said that's 0. So if I were to take it really, really heavy, eventually I'd get something that looked an awful lot like the classical probability. So I've got the quantum one for something fairly heavy on the left, or on the right, I've got the classical probability distribution where we just say a particle is there. And you can see that the classical one is effectively what we would get in quantum mechanics with a very, very massive particle. Now, when we look at atoms, we've got basically a nucleus in the middle, and we've got electrons on the outside, and the nucleus is 1,800 times more massive than an electron. So it turns out its wave function is actually pretty much like that classical distribution on the right. And in many applications, we can treat the nuclei as classical particles. We can't do that for the electrons. Their wave functions really are spread out, but we can do that for the nuclei. And for the same reason that they're more massive, they move at a much slower rate than the electrons. And all that means is, if we think about the nuclei, they're heavy, they're slow, they're kind of boring, they don't do a great deal. Everything that's interesting, all the chemistry, for example, about bonds forming or breaking, or if you're in a metal and you want to know about electrons moving to conduct electricity, it's almost always the electrons. So the nuclei are heavy, slow, and boring, but the electrons are light, quick, and interesting. So if we focus our attention on doing quantum mechanics for the electrons, that's a very good approximation. And it also means that from the point of view of an electron, the nuclei kind of appear static. And this is known as the Born-Oppenheimer approximation. It's a great approximation. It means that instead of having these 2 kinds of particles, nuclei and electrons, I can just focus on the electrons. And it's so useful that I've written a little poem about it. This is my ode to the Born-Oppenheimer approximation. Electrons are light, they travel at pace with wave functions spreading all over the place. Nuclei are not, they're massive and slow. You don't need Schrödinger to see where they go. So that's my little ode to the Born-Oppenheimer approximation, and it might help you to remember it. Okay, So that was the first of my three things to help me. The second is we can concentrate on the lowest energy state, which we call the ground state. Just like if I were dropping a ball, the ground is the lowest it can go. So we say the quantum mechanical state likes to go to the lowest energy. We call it the ground state. And it's a very important state because in everyday life, the things that we're modeling usually don't have a huge amount of energy. So they're not maybe entirely in their very, very lowest state, but they're mostly in the lowest state, and they might spend just a tiny bit of time in a slightly higher state. And most of the properties that we care about really only depend on the lowest energy state. And the great thing about this is if we focus on this ground state, we can use a different form of quantum mechanics, a Nobel Prize winning rewriting of quantum mechanics that was devised by, led by Walter Kohn, and it's called density functional theory. And density functional theory is very clever. What it does is it tells you that instead of doing all of the quantum mechanics with my nasty wave function that has data storage that would exceed the world's global data storage, which is the case on the left here in this box, where all the electrons are interacting with each other and they're moving in this potential that's coming from the nuclei. Now I'm thinking about a material. And if I want to know the energy of that, for example, or I want to know where the electrons are, the electron density, that's really difficult. But density functional theory, or DFT for short, says, well, what you could do instead is look at non-interacting electrons. And the thing about non-interacting electrons is their wave functions, they don't depend on what the other particles are doing because they're not interacting. So my wave function for particle 3 doesn't depend on what 1 and 2 and 4 and 5 and 6 are doing. I can just write that that depends on the position of particle 3. And the only catch is that this now moves in a slightly modified potential. It can be a little bit tricky to get all of the physics that's needed in this potential, but it can be done to good accuracy. And what density functional theory says is that that has the same ground state energy and the same distribution of electrons. And in fact, that means it has all of the same ground state properties. So I can solve this much more simple problem and get exact quantum mechanics. Now, why is this so useful is it's not just that it's a simpler problem. Just look at how simple it is, because the probability density, this electron density, is just how many electrons you expect to find at each point in space. It doesn't depend on which electron is there. It doesn't depend on all the R1, the R2, the R3. Just where am I in space? So in our early example, where we sampled space with a 10 by 10 by 10 grid, this needs a 10 by 10 by 10 grid. It needs 1,000 data points. And it doesn't matter how many particles I have. The total probability is always 1,000 points because it's the same space that I'm sampling. When I add an extra electron to my system, all that happens is it becomes more likely to find an electron there, so the value of the wave function increases, but I still only need to know what the values are at each of the 1,000 data points. And look at what this means. So if I have one particle, ordinary quantum mechanics took 16 kilobytes, and density functional theory takes 16 kilobytes just the same. So it doesn't look a big breakthrough. Now when I go to particle 2, though, ordinary quantum mechanics, I needed 1,000 times the storage because the particles interacted, so I needed to know what particle 2 was doing for every possible position of particle 1. In density functional theory, if I just focus on this probability density, it's still on 1,000 points. I still need 16 kilobytes. 3 particles, ordinary quantum mechanics up to 16 gigabytes, density functional theory still 16 kilobytes. 4, 5, 6, 7. 7 electrons was a good fraction of total data storage in the world with ordinary quantum mechanics, but with density functional theory I'm still at 16 kilobytes. So not only is it much smaller, it's not a problem at all. 16 kilobytes is hardly any storage at all by modern standards. So it makes the problem of the quantum mechanics just enormously more practical. It lets me study not 7 particles, but 7,000 particles. There's not a problem. I can focus my efforts elsewhere in getting all the physics right. So here's an example. This is one of my favorite test molecules. This, if you've done any organic chemistry particularly, you'll be familiar with these diagrams. This is a hexagon made of carbon. Going out as sort of spokes from this carbon hexagon are hydrogen atoms, which are never shown in these diagrams. And then I've added on an oxygen and a sodium. And the reason I wanted to do that is because oxygen and sodium have what's called an ionic bond. Sodium donates an electron to the oxygen, and then they're bonded together because sodium is left with a positive charge, oxygen is left with a negative charge, and opposite charges attract. And the reason this is nice is these are the main kinds of chemical bonding. We've got some covalent bonding where atoms share electrons. That happens between the carbon and the hydrogen. We've got some almost metallic-like bonding around this hexagon, which is what the sort of bars are indicating. And then we've got this ionic bonding, just like is in table salt, that kind of bonding between sodium and chlorine in that case. Every kind of the major bonding is in here. And I'm going to compute the density and see if we can start just telling the computer what elements are where, whether this structure that chemists know, these bonds that the chemists know happen, whether that can come out. So I've done this, and I've done this in a way which starts from a complete guess density and slowly improves it until it satisfies these modified quantum mechanical equations. So you'll see a frame. This is my initial guess. This isn't actually one we normally use because I wanted a really bad guess. Otherwise, the animation's a bit boring. And every frame of this is the computer now trying to improve it and make it closer to solving these Schrödinger-like equations. So every frame here is showing how I'm improving, or how the computer is improving the electron density, and we're done. And you can see here something that looks like a smeared out ring of electrons around the hexagon. That was the metallic-like bonding. Lobes going out to the carbon and hydrogen where the covalent bonding is. Lots of electrons on the oxygen. Lots of electrons on the sodium, but not many in between, because this chemical bonding is not through sharing electrons. So there isn't any high electron density in here. It's because the sodium and the oxygen are charged, and it's those electrostatic charges, the Coulomb charges, which are binding those. I didn't put any of that in. I just told the software what atoms were where, and it told me where the electrons wanted to go. The whole of the chemistry has just emerged from the simulation. Now, in this case, I knew what the answer was, so I showed you the diagram before. But why this is really useful is because we can do this in cases where we don't know what the answer is. It might be a new material. It might be an old material, but under unusual circumstances. It might be under very high pressure, for example. I might want to know what happens in the center of a planet or a star. So I'm going to give you one application here, and this is Chris told you a little bit about this. It's about, can we convert waste heat into electricity? Why would we do this? Well, one reason that you'll almost certainly have come across is because we've got a climate change problem. This is the BP Statistical Review of World Energy. This is the 2017 version. I should probably update it. Since 1960s to the late 2010s, this is the global energy consumption in petawatt hours per year. Okay, not kilowatts, not megawatts, not gigawatts, terawatts. We are at petawatts here, so it's a lot. And you can see that it's just increasing. Just increasing. You can see a little dip in the global recession, but broadly, this is just increasing. We can't sustain this. The planet can't cope if we just keep doing what we're doing with this kind of linear trend in global energy usage. And a lot of the ways that we use electricity, when the electricity is wasted, it's wasted in the form of heat. So one thing that we've been worrying about and wondering is, could we recover that heat? Can we do something with it? And the answer is yes, we can exploit what's known as the Seebeck effect. Okay, I'm going to switch to an animation and see if I can show you how the Seebeck effect works. So the first thing we do with the Seebeck effect is we take a semiconductor, so I've done that in the grey block, and I dope it. So I add some atoms which have one more electron, and I don't add too many. And what that does is it creates a case where the extra electron is quite loosely bound to the atoms I put in. They end up being very mobile. I'm going to color this blue. We call this N-doping, and we usually use blue to mean N-doping. N for negative. I've got some extra negative charge carriers in there. Okay, it's not negatively charged because I've added whole atom, but it's the negative charges that are freest to move around. Okay, how am I going to help this with heat? What I'm going to do is put a hot plate on one end. Now, this is an experiment. In real life, this would be against the device that was generating the heat, maybe your laptop, for example, or maybe you've got a diesel engine in your car still, and that's throwing out heat. So that would be this. But for this cartoon, let's just say there's a hot plate. And then on the other end, there's going to be a cold plate. That might be a big bit of copper, or it might be actually just air or water or something that's cool, cooler than the hot side. And so what I've got is I've got a temperature gradient going from hot to cold. What happens? Well, what happens as I heat it up, as it starts absorbing the energy from the hot side, is all the atoms start moving, and these extra electrons, which are only loosely bound to the atom, well, they start moving around a lot. They start jiggling around in my material. Of course, this is not to scale. They start jiggling around, and when they're near the hot end, they move very quickly because heat, temperature is related to the kinetic energy, the moving energy of the electrons. When they're near the cold end, they move relatively slowly. And that means that after a while, more of the electrons end up in the colder side. Okay, when they go in the hot side, they move very quickly, so they leave quickly. When they're at the cold side, they move slowly, so they leave slowly. And that means over time they build up. Now, at some point, this motion starts to slow down, at least on average. Why does it slow down? Well, notice that now I've got negative charges towards the bottom of my diagram, negative charges near the cold end, and I've left behind some positive charges where they were, and they are, on average, at the hot end, and that means there's an electric field across my material. I've got a positive voltage at the top and a negative voltage at the bottom. So there's an electric field that way, and an electric field that way would like my negative charges to move up. So actually what happens is this carries on until the electric field balances out the temperature field, if you like, until they're roughly balanced. They're still moving around in real life, but they're going as much up as down. So on average, they stay with this distribution. Okay, so everything then stops and nothing interesting happens. Why is this a good thing? Well, it's a good thing because adding atoms with one extra electron isn't the only way I can dope a semiconductor. I can also do what we call positive or p doping. I can add some atoms with one fewer electron, and that means they can accept an electron very easily. And we normally think of this, rather than accepting an electron, we think of this as a positive bubble. So it's just like it's easier to think about a bubble moving through the water than it is to think of there being a bit of nothing. The water is everywhere except inside the bubble. When we introduce this sort of gap in the electrons, it's easiest to think of that as a positive bubble. And why is that a good idea? Well, because when we have our hot plate and our cold plate, they do exactly the same. They move around a lot very rapidly. And they do just what the electrons did. They go from hot to cold. And they also generate an electric field. But because these are positive charges, notice, compare the left and the right. One of them ends up with a negative voltage on the bottom plate, and one of them has a positive voltage on the bottom plate. And if I keep them separate like this, then they'll just diffuse through from hot to cold until the electric field balances it out. But I don't have to do that. If I join them now with some wires, I can make a little circuit. And now what happens is the electrons go from the hot to the cold side on the left, and then because the positive charges have gone from the hot to the cold on the right, the electrons scoot over the wire to the right-hand side where all the nice positive charges are. And actually the same happens in reverse at the top, although I haven't shown that. And I can make a circuit where current keeps flowing, but I can interrupt the circuit with something that I want to do work. In this case, I've put a light bulb in there, an old school light bulb, but it could be whatever you like. It could be a motor, it could be a battery, I could charge a battery from this. This is called a thermoelectric generator. And they really work. You can already buy some. The only problem is they're not really as efficient as we need them to be. So that's what we do with thermoelectric generation. They convert waste heat into electricity, or in fact a temperature gradient really into electricity. They use this Seebeck effect. There's a figure of merit. A figure of merit just means a number that tells you how good it is. It's called ZT, and it goes like this. It's S squared. S is a number that is intrinsic to your material. So it's just a property of any particular material, and it just says how good it is at converting heat to electricity. Then you multiply it by the electrical conductivity. So if it conducts electricity really well, that's good, makes the figure of merit high. You also multiply by the average temperature, because if the average temperature is high, electrons move very quickly. So, and all the holes, the positive charges, they're moving very quickly, so that's also good. And then I divide by this funny K, this kappa. That's the thermal conductivity. And the reason why you divide by that, the reason why a high thermal conductivity is bad, is because you want the hot plate to stay hot and the cold plate to stay cold. You don't want heat to travel from the hot to the cold, because after a while that would lead to both ends being just warm. And then there's nothing driving any of my electric charge. So I don't want that. I want to keep a hot side and a cold side, and that means I'd quite like it to be a thermal insulator, but an electrical conductor. So what I want for a good material is a high Seebeck coefficient, a big S, a high electrical conduction, sigma, a low thermal conduction, kappa. That's what I'm looking for. So the general plan is we find a semiconductor which has a high Seebeck coefficient, and then we dope it, and that introduces these extra easily movable charge carriers, so that increases sigma. And then I want to stop the heat from going too far, so I add some defects which will scatter the vibrations in the material, and that'll lower kappa. That's the general plan. Now, I told you this figure of merit is how good it is. What might that be? Well, at the moment, a commercial thermoelectric might have a figure of merit, this is ZT, of about 0.5. Okay, they go commercially from something like maybe 0.2 up to a really good one might be 0.8. Ideally, I'd like ZT to be higher than that. If I got a ZT to around 1 or higher, that would make it economically, commercially viable for many applications. Of course, the higher the better, but around about 1, it starts becoming really attractive for how much money you would save from regenerating this waste heat as electricity versus how much it would cost to actually make them. And there's a material that's gained a lot of interest over the last maybe 8 years or so, which is niobium, iron, antimony. And it's gained a lot of interest because it has a high numerator, this S squared sigma T, that's known as the power factor, and it has a high ZT. Can we model this with quantum mechanics? This has been found experimentally to be good. Can we model it? So what we did is we solved the Schrödinger equation for this material. I don't have time to go into the details, but we did all the methods of density functional theory that I've talked about. And we mapped out how good this figure of merit is if we dope the material more. So that's what's on the vertical axis here, 10 to the 18, 10 to the 19, 10 to the 20. This is how many doping atoms per cubic centimeter we've added. And I did it for a range of average temperatures. Remember, ZT depends on temperature. And I've gone up to 1000 Kelvin here. If I go too much higher, that starts getting too hot for industrial processes. And if I start going too much lower than 200 Kelvin, remember room temperature in Kelvin is about 300. So what we're used to is somewhere around 290, 300 Kelvin here, down to about maybe on a cold winter's day, 273, 274, 275 Kelvin. And you can see that this ZT goes up to about 0.9 to 1. So this does indeed look interesting. When I do it with DFT, I can explain and understand why experimentally they're getting ZTs that are high, why it looks a good material. But now I can model it. I can start asking, can we improve it? It had a ZT around 1, but only at 1,000 Kelvin, which is pretty hot. I can't use that to recover waste heat on my laptop. It doesn't get up to 1,000 Kelvin, I hope. Okay, 1,000 kelvins, that's over 700 degrees Celsius. That's not where I am. Now, what I could do is I could look at my periodic table and I could think, well, what if I went for something that was a bit heavier than the niobium in the same group, tantalum? And the reason we do heavier is heavier atoms should scatter the atomic vibrations more. Basically, it's harder to move them. So if there's a vibration of atoms moving through my crystal, they'll kind of bounce off these heavier atoms. And why that's important is because these atomic vibrations are how most of the heat travels through the material. So if I can scatter them, I will disrupt how heat is traveling and I'll lower my thermal conductivity kappa. Now, this is quite hard to make, and it's a little bit expensive, tantalum. So we don't want to just tell the experimentalists, oh, we've had an idea. What if you did tantalum? You know, give it a go. Now we can solve the Schrödinger equation. We can predict what should happen. So that's what we did. We predicted, first of all, that you can make this material. The material is stable. It's thermodynamically stable. So it would prefer to have this material than its constituent elements. So that's good. We also predicted that the ZT should increase. And I did the same simulations I did before with doping and temperature, and this is what we get now. Remember that previously for the niobium, we were looking at a ZT of about 0.9 to 1, and that was interesting. But now, look, the ZT goes up to 1.5. So this material that was already very interesting for recovering waste heat as electricity is now 50% better at 1,000 Kelvin. But also interesting is to look at what happens to the ZT 1 or above region, because it's not just that at 1,000 Kelvin it's 1.5, it's also that we're getting a ZT of 1 at a much lower temperature. Look at this, look at the 0.9 to 1 region, this sort of pale green, that's coming in around 650 to 700 kelvins. That's a much more reasonable temperature range for a lot of industrial processes. It's still not quite at the range that I'd like to cool my laptop. So we're going on and we're pushing this study further, and our search now is, can we have something with a ZT over 1 at more like 300, 350, maybe 400 Kelvin, the kind of temperatures that your oven will work at, the kind of temperatures that maybe your CPU in a laptop is working at. But already this is useful for many industrial processes. So our ZT is increased by 50% at 1,000 Kelvin, and alternatively, I can say my ZT1 temperature, if you like, has been reduced from 1,000 Kelvin to 650 Kelvin. So using quantum mechanics, we really can predict the electron's behavior in a way that is practical for a real material simulation. Okay, niobium iron antimony has been made in a laboratory. And actually, after we'd published a paper on tantalum iron antimony, somebody managed to make it. And they've verified that it is, in fact, significantly better than the niobium material. So these are not just calculations in an idealized world or with simple approximations. These really are modeling what materials genuinely do. And we can use them to predict not just thermal conductivity and electrical conductivity for thermoelectrics, but all sorts of other interesting materials. So more recently, I've been predicting new superconductors and high temperature superconductors using alloys involving things like what's called max phase materials. We can do catalysts, so we can look at the chemical reactivity. And we can also take things and put them under extreme conditions. So I've already talked about exoplanetary cores, so large, very massive planets and what happens in the middle. But also we can look at very extreme areas, and we can look at, for example, neutron stars. What happens under immense pressure at very high densities. And what we're discovering is that materials that we might know and love, that we understand what they do very strange things under these conditions. Of course, with neutron stars, the very idea of material is almost broken down. Nuclei themselves might stop being point particles. They might start being strings or sheets, and the electrons might sort of orbit around in cylinders of the string or go above or below these sort of nuclear sheets. So there's all sorts of interesting things in the crust of a neutron star. But even in exoplanetary cores, potassium, for example, which is normally a metal, starts becoming an ionic material, an insulator. Electrons start leaving. It almost looks like a table salt crystal structure with positive and negative ions, but the positive ions are the potassium and the negative ions are just electrons in gaps in the material. So that's my whistle-stop tour of how we do quantum mechanics practically for real materials, and just one of many applications people are doing. If you look online, there are nearly 30,000 papers a year published using this method, many of which developed using the software that we develop in York, applying these principles to give software that experimental scientists and industry can actually use for real simulations for things they care about. Thank you very much for your attention.
That was great, really interesting as always, Phil. Thanks very much for that. That was great. It seems to have inspired a few questions, although I think some of these you might already have happened upon in your final slide. So we'll go through them anyway. So you said that the distribution depends on mass, but one of our attendees has said that they've heard people talking about it to being more to do with size. So what does the probability distribution look like for very small, very dense objects? Is that
Yeah, so if it has high mass, then it effectively the wave function, the probability distribution is very peaked. It looks like a classical point particle. If you've ever looked at how Newton thought about these things, we sometimes talk about the snooker ball or the billiard ball approximation. It's just there. We don't have to compute the probability. You can see where it is. If I turn my back and look and then look again, it's still there. Um, the size is really just because if it's very small, the mass will be very small. And if it's very big, the mass in general will be really big. But there are some exceptions. So hydrogen and helium and lithium, for example, there's not a huge amount of mass there. They're a bit borderline. Occasionally, there are some quantum mechanical effects that I need to worry about.
excellent? We've got a bunch of other sort of. I'm trying to work out if I can include any of these in a single question. How is the Schrodinger equation solved? I guess
Okay,
is that quite technical?
so we solve that numerically. Okay, the full answer is too technical for now, but effectively what we do is we can guess a solution and we can calculate its energy. And then we use calculus, we effectively differentiate the Schrodinger equation. And what we ask is, okay, what is the gradient of the energy as I change my guess? So if you've done calculus, dE by d density is effectively what we're trying to do. We have to slightly do something else. So technically it gets more complicated at this point, but that's basically what we do. And if I know that, I know how the energy changes if I change the density, and that actually tells me the best way to change my density to lower the energy. And remember, we're looking for the lowest energy state. So if that tells me, oh, how could I change the energy quickest, what change the density would be good, I can change the density a bit more. That gives me a new guess. I can calculate the new energy. I can calculate a new dE by d density. Tells me how to change it again, and I keep going iteratively. Every frame of those iteration of the animation was a new guess density. Actually, it's more efficient than that. The human eye is not good at solving quantum equations. It would get there in one frame, but I crippled it. When it said change the density, I said, only change it by 1% of what you think so that I could get an animation. Otherwise, your eye isn't good enough. It takes multiple iterations to get there, but by eye, it almost is instant.
Excellent. Someone's asking if the Schrodinger equation uses a partial derivative. I've just finished teaching a lecture course on partial differentiation, so I presume it does if it's multidimensional.
Yes, yes, and various courses at York
Yeah,
You can go and find out what's online at various colleagues. They're all the information in the lectures we cover in the degree.
excellent. Can you unsolve? I don't really understand what this question means.
Ooh,
Maybe you can. Can you unsolve the Schrodinger equation? So if you're given a density map, can you identify the compound from the density map?
great question. In principle, yes. Now, when a theorist says in principle, that usually means no. So I am a theorist. In principle, yes. Actually, it's being looked at as a form of encryption because, in principle, yes, but it's extremely computationally difficult. So you have something where if you knew what it was, you could go, if you knew what, um, technically it's the atoms create the potential the electrons move in. So what you'd be doing is, can you go from the potential to a density? Yes, you can. That's actually the full density functional theorem. It actually is in terms of potential. The important thing is you need the Seebeck coefficient. Now that's a property of basically how fast negative charges move, how mobile they are. It's actually called the mobility, and what the mobility of positive charges is. And you need there to be an imbalance between them, or between the number of possible states they can be in. That's computable with quantum mechanics. You can say what energy do all these particles have, how many have which energy. That's all you need. Actually, that's about the easiest thing you can do. Next bit, sigma, the conductivity, electrical conductivity. Well, actually, if you know the mobility and you know how many electrons have what energy, that also is not too difficult to compute. You have to put it into what's called an electric transport equation, but actually, it's a lot easier than quantum mechanics. So we use another computer program for that. It's very quick. T is the temperature, so that's fine. That's just what temperature are you operating at, the average temperature. Kappa is the tricky one. And it's tricky for two reasons. One of them is electrons. Electrons carry heat. That's not awful. It's basically the same calculation as for sigma. The tricky one is atoms, or rather the nuclei. The nuclei vibrate, they carry heat as well. I did kind of hint at that when I talked about disrupting the heat by putting heavier elements, tantalum, in this illustration. I need to know how atoms vibrate. To do that, I need to know how does the energy of my system change if I move an atom a bit. dE by dr. Actually, dE by dr is the force. I need d2E by dr squared, which, if you think about this a lot, is like imagining that where atoms normally would go in the crystal, if I move an atom off that, they're sort of tied to the normal position with a spring, and it's how strong is that spring. That's what we're computing. That's d2E by dr squared. And if I know that, I can work out if I give a bit of heat to the system, how will the atoms wobble around their ideal positions, and how they wobble around and how they interact with the other atoms tells me how a vibration would move through the material, and that tells me how heat goes through. But I need d2E by dr squared for every atom in the material, which is not easy. So that is computationally expensive, takes a lot of computer time. You can do it with the software that we develop. Will do that for you, but it's not as simple, not as simple as the Schrodinger equation. Imagine that as a sentence, more complicated. I have to solve effectively a Schrodinger equation per atom.
Excellent. Yeah, I always say it's not rocket science. Rocket science is easy, right?
Rocket science, yeah, that's
It's
right.
quantum mechanics is difficult. Yeah, there's another question about quantifying materials' thermal and electrical conductivity, which is kind of basically what we're already done.
That's pretty much, yeah.
Yep. There was a two questions here kind of related to each other about what happens when you increase the doping. It seems that
Yeah,
ZT increases, but then it starts decreasing again.
yeah,
Is there
good
an
question.
optimum? And is the doping independent of the material?
It's
So there's
not
two
independent of the
questions there,
material. It
right?
does depend. So there are a few things there. One is if you put too many other atoms in, it stops being the original material. So the normal way we think about doping is you have loads of a material and we change just a few atoms. Okay, so if you like, the atoms I've introduced are sort of forced to do what the old atoms would do, but they have a different number of electrons, and that's why they donate an electron or they try and grab an electron, which we usually say they donate a hole. It's these
Yeah.
bubbles. Um, If you put too many in, that approximation, that way of thinking about it is complete nonsense. You've made a different material. You've changed, if you imagine taking a semiconductor like silicon and changing half of the atoms for something else, that's not silicon. Okay. The other problem is if you add too many electrons, too many donors, for example, it becomes a metal. And the reason we did a semiconductor, it didn't go into this, the reason is you don't want a metal, because in a metal, the electrons flow too easily. They carry all the heat as well. So you kind of short circuit the whole thing by you get a really good electrical conduction, but also they carry all the heat with them as well. And so your hot and your cold become two tepid plates. Not very interesting. No temperature gradient. The whole thing stops working. There is a
Yeah.
small effect. You might have come across a thing called a thermocouple. You can, because it's different for different metals, and you can exploit that, and you can generate a little bit of electricity. They're very inefficient, but it does happen. If you doped the semiconductor too much, that starts happening. So there
Right.
is an ideal bit. There is a sort of sweet spot. It's a different for each material, but generally you want to dope it as much as you can before it either chemically breaks down or electrically breaks down, if you see what I mean.
Excellent. How much butter can you put in your carrots before they become unhealthy?
Yeah,
Right.
before they become carroted butter
Carrot
instead
butter
of
rather than
buttered
buttered
carrots.
carrots.
Yes,
Excellent.
exactly.
Okay. Okay. Excellent. Um, Drew, we have. Oh, you said that the CC bond. You see, my undergraduate's in chemical physics. I know a little bit about this. You said the CC bond acts metallic. How is that? Isn't a CC bond a covalent bond? Uh,
No,
yeah.
because it's what's known as a pi bond. So there is, just to keep life interesting, there is also a covalent bond there. So normally what the picture is there's a single bond there, which is a covalent bond, but there's an extra bond which looks a bit like um, every other pair of carbon atoms has a double bond.
Yeah, so this is
Um,
kind of a bit like it's more like a graphene kind of a
it's
graphite
like
type of
graphene,
structure
yeah, graphene
rather
or
than
graphite.
diamond kind of structure, I guess is how I would think of it.
And if
But
you plot the density, did you notice the electron density? There was a sort of a ring, there was a cloud there. That's characteristic of metallic bonding. Electrons are kind of just smeared out. You don't really notice each atom and then a bit of electron shared. They're spread over space. That's characteristic of metallic bonding. Okay. Um, that doesn't prove that it's metal, of course. You could
yeah,
do the conductivity calculation, but it is. It's known as pi bonding. In chemistry, it's sometimes called resonance bonding because the double bond, if you like, could go between carbon atoms 1 and 2, and then 3 and 4, or 2 and 3, and 5 and 6, and
yeah.
so on.
They
And
kind
six
of
is one
yeah,
again,
they kind
round
of
round the ring. So
yeah,
you get kind of
they
three
flip.
pairs. Yeah,
Yeah.
but it's
Plus
just a different way of thinking about the same physics.
excellent. There's someone who clearly knows the literature. I don't know there's a question about the some work done by on thermoelectric material design by Wojciechowski and AGH in Krakow, apparently, I mean, achieving some thermoelectric material developments. I wonder if they use your models. Yeah,
They may well. So it's probably the most popular way of doing thermoelectric modeling. Um, the question is whether it's modeling, materials modeling, in which case density functional theory is the most popular. Um, there are more accurate ways, but much more computationally intensive. Okay. So how could they be more accurate? What I didn't say is the extra potential that you add, we actually don't know exactly what it is. We know some of its properties, we know what it is in certain situations, but there are some approximations there. Um, but it turns out density functional theory is astonishingly accurate for relatively low computational cost. It's not nothing. It's typically about 40% of the UK national supercomputers' time doing this kind of stuff. That's not free. However, it's an enormous amount of science that's done. Whereas if we went to the old way, traditional quantum mechanics, um, we could use 40% for just a couple of materials, not the thousands of materials that we can simulate every year.
so. I think someone slightly misunderstood. So we've got a question about the Schrodinger equation using partial derivatives, i.e. 3D derivatives, but you didn't say 3D necessarily. But anyway,
No.
what are the planes, what are the dimensions being solved
Okay.
such that
So
partial derivatives are required?
it's okay. The real one. So there's lots of ways. In the Schrodinger equation, you would normally write it as three-dimensional space and perhaps time. Although I'm for the lowest energy state, we normally say it's static. So that would be partial dE by dx, dE by dy, dd by dz in density functional theory. In full quantum mechanics, d by dx 1 for particle 1, dy 1, dz 1, dx 2, dy, and that's you can see where the problems start immediately. However, what I was talking about is the derivative of the energy with respect to my guess density. So if I'm modeling my density on a 10 by 10 by 10 grid, which I'm not, that would be, I need to be more accurate than that. But if I were, there are 1,000 points. So my partial derivative is with respect to all 1,000 points. So it's dE by d density at point 1, density at point 2, density at point 3. So it's a, if I were to write it as a vector, it'd be a 1,000 dimensional vector. So don't think too much about what space that would be in.
I'll try and one other. I think because I think you've kind of answered this. Neutron stars are also compact objects where we have to use relativistic models and theories. Um, like relativistic mean field theory. How does DFT work in that case? And does it? Is it
Yeah,
not?
there's a relativistic invariant. In fact, we need to use it for magnetism. That's a relativistic effect. So
Yeah.
we use variations of the Dirac equation. There
Yeah.
are challenges. Neutron stars are difficult.
Horrible things, aren't they? Yeah, we're but lots of other work going on at York on neutron stars, including things like looking at the skins of 10 nuclei to see what pure neutronic material might look like and things, all kinds of cool things. Anyway, and we've just had one person say this has just been absolutely brilliant. Thank you so much from one of the people who that was their question, not really a question, more a comment,
You're
but a very
very welcome.
welcome comment, which was lovely. And we've already hit time, so I mean, it's thanks so much, Phil, for giving this talk. It was really interesting. So all that leaves for me to say is thank Phil once again. It's a wonderful talk. Always a pleasure to hear you talk about your research. Really fascinating. And to wish you and everybody else on the call a very good night. And I'll catch you around at the next webinar. See you then.